So we're working on this plate movements assignment. We've just colored in the Pliocene-Miocene rocks, which are on either side of the San Andreas. They've been moved in opposite directions. So now you have a couple questions about those rocks. How do their locations compare with the direction of the arrows? So on this side of the fault, you can see that the arrow is going to the northwest. On this side, you can see that it's going to the southeast. How do the locations of those rocks that we just colored red, how does that compare to these arrows? Do they match, in other words? Or is there no relationship? Could you imagine if we went backwards in time, went backwards with these arrows, would we see that these two rocks were joined together? We know they're the same age. We know they're the same type of rock. If we went backwards in time, wouldn't they have been formed in the same place at the same way? And they would have been one big mass of rock. However, the fault has broken them apart and they have been offset by, I don't know, a couple hundred miles. So answer that question. All right, next, we can calculate how fast the plates are moving past each other, but by dividing the distance they've moved by the amount of time that they've been moving. Let's look at that for a second. You don't have to write this down. I just want to point out what we're going to do is we're going to take distance over time. This is always going to be the speed of something. Wouldn't this be the same as miles per hour, for example? Isn't miles a distance and hours is a time, miles per hour? That's how we normally measure speed. When you were in physical science, we often measured speed or velocity with meters per second. But here, if we go back, I think it talks about this. We're used to measuring our speed in miles per hour, but the plates move so slowly that we have to measure their speed in centimeters per year. So centimeters are a distance, a small distance. Time, well, that's a year, a pretty good sized time measurement. So we're going to measure distance over time for these rocks to find their speed using centimeters per year. Use the scale in the corner, right down here. Use the scale in the corner of the diagram and a ruler to estimate the number of kilometers that the rocks have moved apart since they were formed. Okay, so this is what, since we're doing this not on a piece of paper, we're not going to use a ruler. Instead, this is what I'm going to do. And follow along with me. Do the same thing that I do. I'm going to activate a line, and I'm going to find the very northernmost point of this set of rocks, and I'm going to start my line right there. Then I'm going to stretch that line out to the matching northernmost part of rocks down here that have been offset. So now I have a line that shows how far they have moved on this map. Now all I have to do is compare that line to this scale of miles. The tricky part is that this line is at an angle. This scale of miles is nice and horizontal. So I am going to do my best to turn this line into a horizontal line without changing how long it is. That's the tricky part, because I could easily accidentally, when I'm straightening this out, see how I made that much shorter? I don't want to do that. Similarly, when I'm straightening it out, I don't want to stretch it longer, right? I went off the edge. Don't want to do that. So what I do want to do is try to flatten this line out by swinging it up, but without stretching it. I'm really trying hard to not stretch it and keep it the same length it started. And I'm probably not perfect, But that seems pretty close. What do you think? From the northern point of each matching rock, I've tried to measure as well as I can. So then I'm going to bring it down here, and I can see that that line is longer than my scale, so I know it's more than 200 kilometers, huh? So I'm going to try to grab this line right here, and right where that little cross is, I'm going to line that up with the 0 and let go. See how that moved the line? And now I can measure the leftover. I know all this on the left side was 200 kilometers because I lined up, I'll do that again. I lined it up with 0 over here. So I know that this much of the line is 200 kilometers. Then I'm going to grab it right at the 200 kilometer mark. I'm going to line that 200 kilometer mark up with the 0. And that gives me my measurement of my total kilometers. So I have to add 200 to wherever the line goes to now. Okay? And I'm going to let you do that for yourself, and you fill that number in here. It doesn't have to be exact. Like this one is, I would say, closer to the 50 than it is to the 100. So I would just call that 150 right there, especially because my measurement was not too precise when I straightened that thing out. I might have stretched it. I might have shrunk it a little bit. So I would just call this much more as 150 more than what I did before. So hopefully you have a number here now. Please tell me if you're not getting what I'm talking about, because we need that number to move on. So talk to me. Okay, I'm going to assume that we're all ready to move. Well, what we need to do next is we have to convert this measurement of kilometers into centimeters. So you're going to take whatever that number was, and you might need a calculator to do this, and you're going to multiply it by 100,000. Or you just take that number and add 1, 2, 3, 4, add 5 zeros behind it, and you'll have the measurement in centimeters. It should be a big number. It should be like what you would like to see on a paycheck. It should be like what you would win in the lotto if you were lucky. Big number of centimeters. Because remember, a centimeter is only about the width of your finger, and we're measuring like a good part of California, right? Almost San Francisco to LA. So, next thing, radioactive age dating shows that these rocks, the Pliocene-Miocene rocks, are 25 million years old. So again, that's much younger than the dinosaurs. The dinosaurs were killed off 65 million years ago. So these are mammal age rocks. This is before humans, but there could have been like mastodons and saber-toothed tigers and stuff. So radioactive age dating shows these rocks to be 25 million years old. We're going to divide the distance that they moved by their age. In other words, we're going to divide distance by time to give us the average yearly speed of movement along the plate boundary. So whatever you got here, whatever answer you have there, by multiplying, you're going to just repeat that same answer right here. Just copy it down again. However many centimeters you got. Then you're going to take this 25 million and you're going to put it over here. Remember, million means that it has 6 zeros. So we're going to have 25, comma, 0, 0, whoops, I'm not writing. 25, comma, 0, 0, 0, comma, 0, 0, 0. 25 million years. Go back to your calculator, punch in this number, divide it by 25 million, and that's going to give us the centimeters per year of movement that occurs along this fault. So you should get a final answer that is definitely less than 10. And that's centimeters per year. So that means in 1 year, at least in the average year, that's how far the fault moves. Okay, then normally, if we're doing this on paper, we'd use a ruler to draw a line showing that same distance, how far it moves in a year. We would measure this many centimeters with a ruler. What I'm thinking is that this scale of miles looks to me like this is about 1 centimeter. So let's draw a line and use this as our ruler to make it the right length. So for example, if I'm moving 1 centimeter a year, if that was my final calculation, I would make a line that is that long down here. That would show 1 centimeter per year. And I don't think you got 1 centimeter per year, but probably not too different from that. So draw a line showing that much movement. Now think about this. This is the whole landscape moving that far in a year. I also want you to think about the fact that it's probably not a smooth, steady movement. It probably moves a bunch from time to time and then doesn't move at all for a long time. What happens when this moves a whole lot at once? How do we experience that? So you're going to draw this line that matches your answer over here. Whatever you got here, you draw that line to match, right? And then, oh, and I'm going to tell you also that there is some variation in your answers. It's not like I'm looking for an exact answer. I'm looking for an answer that's in the right range. So like I said, you should definitely have less than 10. If you have more than 10, then that's a problem. If you have less than 10, then you're good. So we're not going to worry too much about having the exactly correct answer because people get different measurements right here when they're doing this process. But I do want you to write something here. I want you to tell me what's your impression of this average speed of plate movement. And keep in mind that it takes a year to move that far. What do you think of that? Does that seem incredibly fast to you that the plates are moving that far in a year? Does that seem incredibly slow to you, like they're just barely creeping along? What is your impression of that much movement in a year? Again, I don't think you have exactly 1 centimeter like I drew. I was just showing you how to use this ruler to measure centimeters. When you're done, let's take a moment to save your work. And then we're going to move on to page 2. Okay, please tell me if I'm going too fast. Again, you'll have to talk to me because I can't see the notifications. Actually, the speed you calculated is the average yearly movement over a huge span of time, 25 million years. Sometimes the plates move much faster than this, while much of the time they hardly move at all. How do you think we would experience a sudden large movement along the fault? What do you think we would experience on the surface of the Earth if all of a sudden this moved further to the northwest here? How would we experience that? This plate moving along the fault. Hopefully this next paragraph is going to confirm your answer. One of the biggest earthquakes in U.S. history happened near San Francisco in 1906. It was 7.9 on the Richter scale. Much of the city was destroyed, first by the quake and then by a fire that couldn't be put out because the water lines had been broken by the earthquake. It burned for several days. This single earthquake produced an average offset of 5 meters, about the length of a car, all in a few moments. Imagine the land jumping that far all at once. And there's a place where you can go to see this. I'm going to go do another search over here. What is it? It's the offset fence in just north of San Francisco, at a place called Olema, where this fence that was built before the 1906 earthquake, you can see it here, how much it moved during that earthquake. So this fence was not broken apart in the past, right? Come on. It was one straight line. And the earthquake, it's kind of incredible. It didn't knock the fence down. Instead, it just offset the fence and split it into two sections. And I'm not able to get up here. Can I move this? Nope. Okay, I'm just going to go back one more chance. Yeah. Okay, so 5 meters offset all at once. Okay. Let's try to figure out how often an earthquake of that size would happen in order to separate those Pliocene-Miocene rocks as far as they've moved. So what we're going to do now is we figured out how many centimeters per year. We also know how far the big earthquake of 1906 had movement along this fault, 5 meters, all at once. Now we want to see how many earthquakes of that size would it take to move these rocks this far in 25 million years. How often would those big quakes occur? So you're going to take this number back here that we had before, this huge centimeter number. Sorry, I keep going to the wrong page. You're going to take that big centimeter number. Oh, I take that back. You're going to take the kilometer number, this one. I'll put a circle around it. We want this number, and that number you're going to carry down to page 2. It should be something 100 kilometers. You're going to put that back in here. Repeat that number, something 100 kilometers. Multiply by 1,000 so we can convert that to meters. Because we know that the quake moved the rocks 5 meters in that one instant, we want to measure in meters. So we're going back to what we measured from the map right here, several hundred kilometers, times 1,000 to convert it to meters. Then you're going to take this number, carry it down here, and divide by 5 meters, because that's the offset of the 1906 earthquake. We know that one big earthquake moved the land 5 meters. So the question becomes, how many earthquakes would occur in that amount of time to move the land that far? How many of these big earthquakes would happen to move the land this many kilometers? We've measured that it's moved this far. We know this for sure. We also know that one big earthquake had this much offset. So how many big earthquakes would be required to move the land that far? And that leads to the question, so hopefully you've done this division now. Again, you got to talk to me if I'm going too fast. So we take that number of quakes and we want to find out how often they occur. Isn't that something that concerns people a lot? When is the next big earthquake going to happen? So we want to try to come to a measurement of how often these quakes actually happen. So remember that this movement took 25 million years. So we found the number of earthquakes that occurred during that time. I think it's several thousand. To find the average number of years between these big quakes, just divide the years it took to move the rocks apart by the number of quakes. So we're going to take our 25 million years here. Again, 25 with 6 zeros. That's going to go down in this space. Then we're going to take the number of quakes that we just calculated. We're going to put it in here. Punch them in your calculator, divide, and that tells me, or tells you, how many years occur between each of these big earthquakes. And remember, we're only talking about the big ones here, the 7.9 earthquakes. And when you're done with that math, answer this question: what's your impression of how often these occur? All right, I'm going to pause for a minute and please give me a thumbs up if you're staying caught up with me. Let me know how things are going. Thanks, Gabby. All right, Kevin, I love your use of different icons. Thanks, Andres. I remember that from last year now, Kevin. Thanks, Kaylee. All right, so if we're staying caught up, that means we're ready to move on. Tell me your impression of how often these occur. Next, does the number of years between big earthquakes follow a regular pattern like the phases of the moon or solar eclipses? We can predict when those are going to happen. Those we know are going to happen on these days, and we can predict well in advance. Like there was a solar eclipse that just occurred in Antarctica, and a lot of people went down there to see it. They were able to plan ahead because they know exactly when it's going to happen. It follows a regular pattern. The phases of the moon, that's once a month, it's a full moon again. So very regular pattern. So are earthquakes like that? Do they follow a regular pattern? Or are they more random, like a flood or a hurricane? Can we tell in advance exactly when those are going to happen? Can we say, oh, I'm sure that on March 13th, 2022, there's going to be another big snowstorm? Am I able to say that this far in advance, or is it more random than that? Are we guaranteed to have a big quake when the numbers of years you have calculated above have passed? So this is a two-part question. First part, what do you think? Do the earthquakes follow a regular pattern or are they more random? Second part, you calculated this number of years up here, whatever that might be, which I think is in the several hundred range. Are we guaranteed to have a big earthquake when that many years have passed by? I don't know, let's say you got 350 years between earthquakes. Does that mean that since we had one in 1906, the next one will definitely be in 2256? And that takes us to the next question. The average yearly movement on the fault is quite small, and there are many years between big quakes. Does that mean that residents in California have nothing to worry about from the fault? Please explain your answer. So, if you agree with me that the earthquakes are hard to predict, they're pretty random, and this answer up here, the number of years between big earthquakes, that is an average number. It's not a certain thing. Some years, it might be, I don't know. I don't mean to say some years. I mean, sometimes instead of being every 350 years, it might be twice that much. It might not have one for 700 years. On the other hand, in another time, it might have three in a row. Might have one in 2032, 2033, and 2034. Might get three big ones in a row. But the average ends up being 350 years between big quakes. Again, that might not be your answer, and that's okay, but it should be kind of like that. This is the average number of years, right? Does this mean that California residents have nothing to worry about from the fault because, it says that we won't have another big one for another couple hundred years? Please explain your answer. Okay. Now that's the first half of this project on measuring movements of the plates. It was about the San Andreas Fault and these earthquakes. The second half is about measuring movement of the Pacific Plate at Hawaii. And what I think we should do is wait on this one because I would hate to get like halfway through it and then get stuck and not be finished. So we're going to wait on this until Friday to do this. And instead, we're going to change gears. So save your work, go back to Teams, and find the other assignment called the Ring of Fire. And open that assignment up. Ring of Fire. I'm going to find it on my drive here instead of in Teams. But you go back to Teams to find the Ring of Fire. Oh, I don't mean to do that. That's a recording of presenting at another time. All right, so it should look like this. This is a pretty quick assignment once you figure out how to do it. So I'm going to show you how to do it, and then you're going to be able to finish it on your own. Once again, I'm going to ask for like a thumbs up so I know that you're ready to move on. Or you can just talk to me. Thanks. All right, all right. Okay, so the Ring of Fire. Let's put your name on it to begin with. And then we'll look at the background information here. There are more than 1,500 active volcanoes in the world. An active volcano is one that's erupted at least once in the past 10,000 years and is likely to erupt again. So this is amazing. If it's active, it's erupted within the last 10,000 years, and that's still considered active. It might have been sleeping for 9,000 years, but we still consider it active. We have to remember that in terms of the Earth and geology, time is a lot different than it is in our human lives. 10,000 years is quite short for humans. Excuse me, for the Earth. It's pretty long for an individual person, right? But for the whole Earth, that's not very much time. Because most of the Earth's volcanoes are hidden under the oceans, people have not been able to witness their eruptions. Every year, about 50 or 60 volcanoes erupt on land where people might be able to see them. A volcano just erupted in Indonesia. Let's see, I think there's a map on page 2. Over here, Indonesia, a volcano just erupted there a week ago and killed like a dozen people. Meanwhile, there's these 50 or 60 that erupt on land, but scientists estimate that there are about 200 volcanic eruptions under the oceans every year. So this is what we're going to do. First of all, number 1, choose 3 colors to represent the 3 different kinds of volcanoes. So we have 3 kinds of volcanoes. This is your introduction to them. Stratovolcanoes have many layers. The word strata means layers. And these form during different kinds of eruptions. So maybe one time it erupted lava and made a layer of lava. And then the next eruption was ash, and it covered the ash covered the lava. So we have a new layer. Then it made another layer of lava. Then it had what we call a mud flow, which covered that older lava. So we have these multiple layers in stratovolcanoes. They generally grow really big. Shield volcanoes are gently sloping volcanoes shaped like a shield laying on the ground. So imagine a warrior's shield from the ancient days and laying that on the ground. So it's kind of a gentle slope, not at all like this diagram here. This one is more like the third type of volcano, a cinder cone. It's a cone-shaped volcano made of bits of hardened lava or cinders, and these usually go flying out of the volcano in separate little rocks, and they build up into this steep cone. Okay, so you're going to choose 3 colors, move on to page 2, and fill in the different colors that you're going to use. I'm going to make a square. I'll show you what I would do for the first one. Make a square for stratovolcano, and I think I'm going to make that be a red square. I'm going to right click on it. I'm going to click on properties, and I'm going to change the fill to also be red. So we're going to do that for the stratovolcano, the shield volcano, and the cinder cone. Choose 3 different colors. This part, the ring of fire, is already filled in for you. The striped region in this map is the ring of fire. And you can see it circles around the Pacific Ocean. You can also see that there are lots of volcanoes in that ring of fire, which gives it its name. So you're going to choose 3 colors to represent those 3 types of volcanoes. Next, we use this table. Look here, volcano number 1, named Azul, is a stratovolcano which last erupted in 1967. So what you do is you go down here, you find volcano number 1, and I need red to represent that volcano. So I'm going to make a red circle. I'm going to try to make it the same size. It might help if I zoom in here. Makes it a little easier to be more precise. Once again, right-click, Properties, fill it in with red, click OK. Now I'm going to drag that over here. There's volcano number 1, a stratovolcano. Azul is its name. But the point here is the type of volcano. Now, for my next stratovolcano, the easiest thing is to click on this and use the copy-paste tools. Shortcut Control-C, to copy, Control V to paste. Or if you have a Mac, it's Command C and Command V. So I am now ready to put this guy, this circle, on the next stratovolcano. So there are like, what, 24 of these, right? Number 2, Bezimlanmi, I've not heard of that one. 1993, also a stratovolcano. Go back to my map. Oh, there it is up there. It's part of Russia, part of Siberia on the Kamchatka Peninsula. So number 2, also a stratovolcano. I can just drag that red circle that I copy pasted over there. All right, so that's the first part of this assignment, and I'm going to turn you loose to work on this in a minute. You just assign these colors to the different volcanoes, right? Let me show you what you're going to do next. You're going to do some math. You got to calculate percentages. So percentage is the number in the category divided by the total number times 100. So if we look over here, oh, there were 24 total, huh? Let's say that out of those 24, 12 of them were stratovolcanoes. This is not the answer. I'm just saying, let's say that was true. Now, can you do this math in your head? 12 out of 24, isn't that half? Doesn't that mean it should be 50%? So if you put in your calculator 12 divided by 24, and then multiply that by 100, you would get 50%. All right, so take however many there are divided by 24 to fill in this chart. Similarly, for this chart, you're going to find a percentage again, but now you got to figure out how many volcanoes are in the ring of fire and how many are not, how many are outside of the ring of fire. So you'll have to go back to your map and count the number of volcanoes in the ring of fire versus the number that are not in the ring of fire. So we know there's a total of 24. You just start counting 1, 2, 3, 4, 5, etc. until you've counted all the ones in the ring. Divide by 24, multiply by 100, and you will have your answer for this one. Okay? Oops. Then there's just these 3 required questions and a bonus question, and you'll be done. So this is your homework due on Friday. I'm going to give you the rest of the time to work on this if you like. We will also finish the plate movement assignment during class on Friday. Okay, so if you have any questions, let me know. Other than that, you are free to go, and thank you for being here. Thank you for participating, and thank you for being on time.
Later, Fairly. Thank you.
All right, thanks for being here, guys.
Bye, Fairly. Thank you.
See ya.